Hey guys, I just wanted to give you some notes, kind of like as if we were in class. You have to let me know if you like this format or not. I'll put a link to the slides below too, so if you don't want to hear me, you don't have to watch me. But anyways, the notes today, we are starting the new unit, and you guys did the experiment yesterday with the metal and the plastic, and hopefully it was a really cool thing that we would have done in school. And tomorrow, when you'll get to see an explanation of what was happening in today's lesson too. So what we're doing right now is called thermochemistry. So we're looking at energy that's involved in chemical and physical changes. And one of the first things that we want to talk about is what is heat and what is temperature. A lot of times these two things get used interchangeably, kind of like weight and mass when you took physical science. They're directly related to one another, but they're not the same. So temperature, we know this from KMT. It's the average kinetic energy. It's really directly proportional to the motion of the particles. So it doesn't matter what the size of the sample is. It's just going to take the average of the vibrations or the jiggliness. If you remember the video that explains the difference between hot and temperature and heat, kind of talks about temperature being measuring jiggliness or movement. And we know that temperature is measured in units of Celsius. We know we can convert easily to Kelvin. In the United States, we use Fahrenheit. So those are temperature units. And then heat is different. Heat is energy. And if you remember from physical science, energy is measured in units of joule. So joules, and then there's 1,000 joules in a kilojoule. Calories are another energy unit, and we know that a kilocalorie would have 1,000 calories in it. And actually our food calories, like if you read on the box of pasta, I think it's 200 calories for a serving. It's really 200 kilocalories. Food calories are actually really kilocalories, but it doesn't really matter because everything is given in that notation. So we're going to talk, I just want to talk to you briefly about what a system is and surroundings. So a system is whatever we're focusing in on. Like the experiment that you did at home, the system was, I'd say, the ice, and then the surroundings would have been everything else. So we were looking at the melting of the ice in the surroundings. And what we do in thermal chemistry is we assume that all of the energy that is given off from one system, and we use a negative to show that the energy was released, is going to be then absorbed by another system. So give you some examples of this. So if I have my coffee in the morning, the heat is going to flow. Heat is going to always flow from warm to cold temperature. So the heat from my coffee, which would be the system, is going to go into the surroundings. But yet if I have my my Coke Zero, that's nice and cold, the heat from the room is going to flow into the Coke Zero. So the value, like let's say my coffee loses 100 joules of energy, so it'd be a negative 100 joules, is going to then equal the amount of energy the surroundings gained, which would then be positive 100 joules. So think about like melting ice and water. The systems that we're focusing in on here would be the ice and the water, and which way is energy going to flow or heat flow. So the system is the ice and the water, and the energy is going to flow from the warmer to the colder. So it's going to go from the water into the ice. So kind of back to the differences then between heat and temperature. heat is energy, temperature is the movement, it's an average of the kinetic energy of the particles, and they're directly related to one another. The heat is the energy flows from a hot to a cold area. Temperature will increase and decrease when it is heated or cooled. So when we do the measurement, like I showed you earlier with the energy, the negative, whatever is being lost is then going to be gained. We use something called a calorimeter. And this video kind of explains what a calorimeter is a little bit better than I can. So I'm going to let you guys watch
It's virtually impossible to know how much heat an object contains, but when heat moves, we can figure out how much heat moved and in which direction. Calorimetry is the precise measurement of heat flow into or out of a system for chemical and physical processes. To do calorimetry, we need a piece of equipment called a calorimeter. This is a calorimeter. It can be made of really expensive materials and be incredibly efficient at insulation. Or it can be a styrofoam cup and do a darn good job of insulation as well. All you need to do this at home is 2 stacked styrofoam cups, a thermometer, a lid, a stirrer, and a known volume of water. Let's say you have all of this ready to go, and you've read the initial temperature of water. Then you'll take a hot piece of copper, maybe let's say at 90 degrees, and drop it into the calorimeter. As you stir, you'll see the temperature rise. Eventually it will stop rising when it's at equilibrium, meaning the water and the copper metal are at the same temperature. The heat given off by the metal is absorbed by the surroundings, which include the water, stirrer, cup, and even the thermometer itself. The majority of the heat will be transferred to the water, and for the sake of simplicity, we'll do calculations assuming that all of the heat is actually transferred to the water. We'll try a calculation to figure out the heat transfer at the end of this video. Often you'll come across...
So if you noticed at the end of the slide, they were talking, let me grab that, I want to show you. Right here.
Water. We'll try a calculation.
She's saying that the amount of energy, there's a negative Q of the metal, the amount of energy that the hot metal lost is going to be absorbed by the water. So we're assuming that all of the energy from the metal goes into the water until they are both the same temperature. So now I'm going to show you a quick video about specific heat, also known as heat capacity.
Okay, Year 11, today we are going to learn about what specific heat capacity is, and hopefully by the end of this video you'll have a better understanding of what that phrase means. I want you to imagine you're at the beach, and here we've got the sun, and the sun is giving the same amount of energy to both the sand and the water. But even though it's the same amount of energy, you'll notice that the sand actually heats up a lot quicker and to a higher temperature than what the water does. So even though the same amount of energy, the sand will have a larger rise in temperature than the water. This is because when we put the same amount of heat into some materials, it actually gives a bigger temperature rise in one than it might in the other. So let's use another example of this. If we have 2 beakers and we put the same amount of water in one as an amount of oil in the other, let's say 1 kilogram of each, water and oil, and we heat both of them for the same amount of time at the same temperature, what we would actually find in this experiment is that even though we've got identical volumes of water and oil, and they're both heated at the same amount of time, so for 1 minute, the oil will actually heat up to 60 degrees while the water will only heat to 30. So the same amount of heat produces twice the temperature rise in oil than it does in the water. To make the water reach the same temperature as the oil, we would have to add twice the amount of heat to the water. This means that water has twice the capacity to absorb and store heat energy as the oil. So we say that water has a higher heat capacity than oil.
So this is also something that I find when I heat food in the microwave, especially when I'm heating like mashed potatoes or something, and then maybe like a meat. They get done, the potatoes take a lot longer, and I believe that's due to probably the high moisture content, because water itself has a pretty high specific heat or heat capacity. That's why it takes a long time to heat the water, like in our lakes, up warm enough for us to actually want to swim in them. The ground and things nearby can be very warm and warmed up, but the water takes quite a while. It also takes quite a while to cool down, so it just wants to kind of hold its heat more so than other things. So, a metal like copper is going to have a very low heat capacity. So that would be, if we were to heat up copper, it's going to heat up very quickly and easily. So using heat capacity or specific heat, we can calculate the amount of energy Q that's lost or gained with a temperature change. So here we have delta T, or change in temperature, which would be final minus initial temp. The C is the specific heat or heat capacity, and this is a constant. We would never ask you to memorize these. Every pure substance has a value for its specific heat. And then the mass of the substance. There's different units you can use for specific heat. We're going to be using joules per gram degrees Celsius, so our mass has to be in grams, and our temperature would have to be in Celsius. So, one more time, just to kind of review, heat energy that is released or lost, which we'll use a negative to denote that, is going to equal the heat energy that is gained or absorbed. So, for example, the calorimetry problem, or in the video, was they were heating copper. So the copper lost a certain number of joules, let's say 2,500 joules of energy. Then the water that the copper was put into would have absorbed 2,500 joules of energy. So I hope that helps. And then there's some other learning to do today too.